A polynomial function only contains non-negative integer powers of its variable. This is a polynomial function because the powers on the variable are 5, 2, and an implied power of 0 because negative 2 is the same thing as negative 2 times x to the 0. This is another polynomial function. The powers we see on the variable are 3, 2, and an implied power of 1 on x, because x is x to the first. The degree of a polynomial is the highest exponent of its variable. Function f of x is of degree 5, because that's the highest exponent we see. And g of x is a third degree polynomial. The leading coefficient is the number multiplying the highest exponent term. Our function f has a leading coefficient of 4, and our function g has a leading coefficient of negative 1/2. The degree and the leading coefficient of a polynomial can help us predict the end behavior of the polynomial. There are 4 possible cases we have for end behavior. If we look at the leading coefficient, which is either positive or negative, and we look at the degree of the polynomial, which is either odd or even, we can use those 4 things to determine what direction the ends of the graph of the polynomial will go. This chart shows us the 4 possible directions for the ends of a polynomial's graph. Let's see if we can break this down a little bit. Suppose that the degree of our polynomial is odd. If that's the case, then the ends of the polynomial will go in opposite directions. Now suppose the degree is even. In that case, the ends of the polynomial will go in the same direction, either both up or both down. If the leading coefficient is positive, then we know that the right side of the polynomial's graph will be pointing up. And if the leading coefficient is negative, then we know the right side of the graph will be pointing down. We can use information about end behavior to help us graph a function. But what if we already have the graph? What does the graph tell us about the degree of the function and its leading coefficient? This is a graph of 3 functions that have something in common about their degree and their leading coefficient. If we look at what's happening on the ends of the functions, we can see that the ends are going in opposite directions. That's enough to tell us that all of these functions are of an odd degree. If we look at the right end, we can see that it's pointing up in a positive direction. That means that the leading coefficient of each function is also positive. Now let's compare what we've predicted to the actual equations of the 3 graphs. The green line is f of x equals 3x. It's an odd degree function because it's a first degree function, and the leading coefficient is a positive 3. The blue function is this one. It's a cubic function, so it is an odd degree function, and the leading coefficient is a positive 2. And the purple function is this one. It's a 5th degree function, so its degree is odd, and its leading coefficient is a positive 1. Here's another 3 functions graphed together. What do we notice? We can see that the ends do go in opposite directions, so that tells us that these are all odd degree functions. If we look at the right end, we see that that's pointed down in a negative direction. So the leading coefficient of these functions must be negative. Now here's the equations for the 3 functions. The green line is f of x equals negative 3x. It's a first degree function because the power on the x is a 1, and the leading coefficient is a negative 3. The blue function is this one. It's an odd degree function because the highest exponent's 3, and the leading coefficient is a negative 2. And this is the purple function. It's an odd degree function because it is a 5th degree function, and the leading coefficient is negative 1. Here's another set of 3 functions. Let's see what they have in common. If we look at the ends, we can see that both the left and right ends are pointing up in the same direction. That tells us that these are all even degree functions. If we look at the right end, we see that it's pointed up in a positive direction. That tells us that the leading coefficient on all these functions has to be positive as well. The equations of the functions confirm what we just predicted. The green function is the parabola f of x equals x squared. It's a second degree function and its leading coefficient is positive 1. The blue function is this fourth degree function. It's an even degree of 4 and the leading coefficient is positive 1. And the purple function is this one. It's a sixth degree function, so it is also an even degree, and its leading coefficient is a positive 4. Let's look at one more set of equations. We can see that the left and right ends on all these functions point in the same direction, down. Since they're in the same direction, we know that these are even degree functions. And since the right side points down, we know that the leading coefficient is negative. This is the equation of the green function, f of x equals negative x squared. It's an even degree function of degree 2, and its leading coefficient is negative 1. Here's the equation of the blue function. It's an even degree function because it's of degree 4, and its leading coefficient is negative 1. And here's the purple function. It's an even degree function of degree 6, and its leading coefficient is negative 4. So what we've just seen is that if we know the degree and the leading coefficient of a function, we can use that information to help us predict what the end behavior of the function will be. Or if we know the graph of the function, we can use that to predict something about the degree and the leading coefficient. That doesn't tell us anything about what goes on in the middle of the function, how many wiggles it'll have. That sort of information we'll have to use other methods for, like looking at intercepts or looking for zeros of the function. But knowing something about the end behavior of a function can be an important tool when we're trying to either graph the function or find out information about the equation of the function from the graph.